In this final chapter of our course, we're going to talk about how to use data that is obtained from samples to make decisions about a claim made about a parameter for the population. This is called hypothesis testing. In this chapter, there are more than 3 sections, but in our course, we are going to cover only the first 3. First, we'll talk about some basics of hypothesis testing. Then we'll talk about how to test a claim regarding a population proportion. And then we'll end with the third section, testing a claim about a population mean. In this introductory section, we will present some components of a formal hypothesis test. These concepts will be general and will apply to all types of hypothesis tests. In our course, we're going to talk about testing claims about population proportions and about population means, but there are other claims that could be tested as well regarding standard deviations, variances, and other parameters. First, let's talk about some of the terminology. In statistics, a hypothesis is a claim or statement about a property of a population. So it's some sort of claim about the value of a population parameter. A hypothesis test, also called a test of significance, is a procedure for testing a claim about that population parameter. There is an example in our textbook that we will use throughout these notes. It is from your chapter problem, and there is a statement or a claim that most internet users utilize two-factor authentication to protect their online data. So that is the claim, that most internet users utilize this type of authentication process. Using lowercase p to denote the proportion of all internet users who utilize two-factor authentication, p here is a population proportion, right? It's a parameter, and the claim is about that parameter. Saying that most internet users used two-factor authentication is the same as saying that more than 50% of internet users utilize two-factor authentication. So most is going to be translated as saying the proportion is greater than 50%, or in decimal form greater than 0.5. So this is going to be the symbolic form of this claim that most internet users have the two-factor authentication for security. Now, in the big picture, we have this claim that the population proportion P is greater than 0.5. Let's say we have a sample of 926 consumers. How many of these would need to utilize two-factor authentication for us to be very convinced that the claim may be true? Would we need to have half of them use two-factor authentication? Probably that wouldn't be enough, because the claim is that most people do. Would our sample need to have just slightly over 50%, such as 464 out of the 926? Well, that's only 50.1%. That's really close to half. So being barely more than half really doesn't make us feel very confident about using the word most. So we really need to have a sample result that is so strong and that is so far from where our claimed value is that we would consider it to be significant. And in this case, we want a significantly high result for our sample. For example, what if out of the 926 consumers in our sample, all but one use two-factor authentication? So that's 99.9% of the sample. Well, I think that would make us feel much more confident that the claim that most people have two-factor authentication may be true. So you see how two different sample results lead us to two different comfort levels in terms of how strongly we believe the claim to be true. When we get a sample result that is kind of on the threshold, very close to the cutoff point, we don't have an extreme enough result for us to feel confident in saying that the statement is likely to be true. Whereas if we do get a sample result that is quite extreme, in other words, significant, then it gives us more confidence that the claim may indeed be true. The question is, well, where is that cutoff point where we stop kind of second guessing the results and start feeling confident? Do we feel confident once we hit 55%? Maybe we can feel confident if our sample ended with 53% of internet users saying that they use two-factor authentication. Do we need to be at least 60%? So where is that cutoff point? And that is why we need a formal method that we all agree on so that the answer to that question can be repeated from one researcher to the next. So we're going to talk about a formal method for answering this question as to whether our sample result is extreme enough, significant enough for us to use it as evidence that the claim may be true. Now we are going to be able to use our calculators to do some of the heavy lifting for us. And in this video, we'll hint at it a little bit, but I'll probably have to post a separate video to show you how to use the calculator commands to generate some of the values that we're going to see here in the slides. I also will be posting a separate PDF document that shows you a model for how I want these problems written up manually. So in this example, this is a screenshot of what the TI-83 or TI-84 calculators would produce if we used the calculator to run a hypothesis test for this very problem. We would find a command called the one proportion z-test. We'll talk about why it's a z-test in just a little bit. The claim here is that the proportion in the population is greater than half, greater than 0.5. The z-score that corresponds to our sample result, to whatever we saw in those 926 consumers, that z-score is what this p-hat gets converted to. So p-hat is going to be our sample proportion. Z is going to be the corresponding z-score. And this p here, it's quite confusing. This lowercase p is what we will know as a p-value. We haven't discussed that yet, so just kind of hang on to that question and we'll address it a little bit later on. So there's a lot of p's going on here, and we actually have a slide dedicated to just sorting through all the various symbols. But this is just a quick snapshot of what your calculator could give you if you used it to run a hypothesis test. Of course, the emphasis is always on making sense of those calculations. So the screen here displayed a test statistic of z equals 1.25 if we round that z-score to 2 decimal places. And it also gave us a p-value of 0.1059. And we're going to make sense of these two calculations later on in this presentation. So we want to make sure we focus on understanding the procedure, understanding what these calculations really give us, and making sense of how we're going to render our final decision. The technology really is just a computational aid. Hypothesis tests, also called tests of significance, will hopefully make use of what we've seen over and over again throughout our course, which is a way of identifying whether sample results are significant or simply they were expected, not surprising. So we're going to revisit the idea of results that are significantly low or significantly high. In this chapter, we're going to formalize those concepts in a procedure that we all agree on. And they have a lot of different applications in various fields. This is one of the reasons that this introductory statistics course is my absolute favorite to teach. Of course, I prefer to teach it in the classroom where we can get engaged in more discussions, but literally the tools in this course, and in particular in this chapter, are used in psychology, in sports, in manufacturing, in business, in education, in the arts, you name it. If there's a decision to be made based on data, these skills are going to be useful. Let's move on to talking about the two different types of hypotheses. First, we have the null hypothesis. The null hypothesis is denoted by a capital H with a little 0 subscript, and this is actually read as H naught, N-O-U-G-H-T. So not the N-O-T naught, it's actually German for 0. So H naught is how we symbolize the null hypothesis. The null hypothesis is a statement that the value of a population parameter, such as a population proportion or a population mean, that is equal to some claimed value. So the null hypothesis is always a statement of equality. We're going to see the equal sign in the null hypothesis. The null hypothesis, while we're here, I'll mention, is kind of the counter claim. So it is what we believe to not be true. It runs contrary to the claim in a hypothesis test, but it will always be a statement of equality. On the other hand, the alternative hypothesis, which we can denote with a capital H and a little 1 subscript, or sometimes we use a little a subscript or a capital A subscript. The alternative hypothesis is a statement that the parameter has a value that somehow differs from the null hypothesis. So the alternative hypothesis is always a statement of inequality. And usually the original statement that we're trying to test is in an inequality format. So we will use one of the following 3 symbols. It will either be the less than symbol, greater than symbol, or the not equal to symbol. So again, these are statements of inequality, not equal. Notice that the 2 inequality symbols here are not the weak type, they are the strict type. So we're not going to see less than or equal to or greater than or equal to, because again, no equality is assumed here. So we will use either one of these strict inequalities or this one that is simply saying, nope, not equal to it. We're not going to say if it's greater than or equal than, greater than or less than, but we just know it's not equal. So very important that you early on make that connection that the null hypothesis is a statement of equality and that the alternative hypothesis is a statement of inequality. Now this is a snapshot from your textbook, and the print is very small, but I think it is a good reference about the process of a hypothesis test. I'm able to really trim down my write-ups for these types of problems to 5 steps. So it's very lengthy here because it shows all the possible routes that you can take to perform a hypothesis test. But if we really trim it down, we can get it down to 5 steps. The first step here is you identify the claim and then you assign it a symbolic form. So usually the claim is going to become your alternative hypothesis, and from that you're going to generate the corresponding null hypothesis, which is the statement of equality that corresponds to it. So really what they have here would be my second step, because they didn't write it here, but my first step is always to write what your symbols are going to stand for. So for example, in this chapter problem that we've been talking about, I would start off by writing, let P denote the proportion of all internet users who utilize two-factor authentication for online data security. That would be my very first step, is to actually write what the symbol stands for. Then my step number 2 would be to write down the null hypothesis and the alternative hypothesis in symbolic form. Next, you're going to choose a significance level, and usually because this is a course where we're starting to learn how to do this, these are going to be chosen for us. But in real research, this selection of a significance level is going to be made by the research team, and it is carefully chosen based on the risks involved in being wrong and getting the wrong conclusion. So it's not something that's chosen arbitrarily. For example, if we're conducting a test on a new drug where we really want to make sure that the side effects are minimized before we approve them through the Food and Drug Administration, our significance level would be very different than if we're running a test on whether, let's say, giving students a treat before taking a math exam helps them perform better. You know, not as consequential as, of course, launching a new drug to the market. So again, this will be chosen for you for the problems that we'll see in this course, but in the real world, this is something that would be carefully selected by the research team. The next step is you're going to identify which test statistic to compute. Really, for our purposes, it's going to be either a z-score or a t-score. So Z is something that we've been working on since chapter 6. T is something that we just introduced in chapter 7 when we were building confidence intervals, but it's going to be one of those two test statistics. Then you have two different options for how you're going to decide if your sample result is extreme enough for you to claim that you have evidence in favor of your original claim or not. So we have the p-value method, which we'll discuss in detail in just a bit. And then we have the critical value method, which more corresponds to what we did in chapter 7. Now, the two methods are equivalent in terms of how much work is involved, and I am not going to necessarily ask you to choose one over the other. But it would be good for you to learn both methods because we do want to conceptually understand that they do lead us to the same conclusion, and also just gives us choices as we go through a full hypothesis test. And then the last step is to interpret the p-value or interpret how our sample result compares to the critical value that was found in order to render a decision as to whether we believe the null hypothesis is true, whether we believe the null hypothesis is not true, and really just make a decision about what our evidence is suggesting. Back to our example, I kind of talked through some of these slides coming up, so I'm going to go through them a little bit more quickly. I said that my first step is always to write down what our symbols stand for. So I'm going to start by saying that lowercase p is going to denote the proportion of all internet users who use two-factor authentication. So it's a claim about the population proportion. Then we're going to symbolically write down the null hypothesis and the alternative hypothesis. Let's spend a little time talking about that here. The original claim was that most people use two-factor authentication, most, meaning the claim is that more than half, more than 0.5 do. Well, that's a statement of inequality. That means that that's the alternative hypothesis. So we can write H sub 1 or H sub A, and then this colon symbol, right, the double dots. Our alternative hypothesis is that the population proportion is greater than half, greater than 0.5. Remember that the corresponding null hypothesis is a statement of equality. So the null hypothesis, H naught, is going to state that P is equal to half. The number that you have appearing in your alternative hypothesis has to match the number in your null hypothesis. The only thing that's going to differ are the symbols. Inequality for alternative, equality for the null. Next, we're going to talk about the significance level. Again, I mentioned that for the purposes of our problems, the significance level will be chosen for us. Now, the significance level, which we denote with a Greek lowercase letter a, which is alpha, that significance level alpha is equal to the probability of making a mistake, which is rejecting the null hypothesis when in fact the null hypothesis is true. So there's always a risk that the evidence will point us to the wrong decision. The truth is, we never know if we've made a mistake, because if we knew the true value of P, we wouldn't have to test a claim about it. So P is an unknown value, and all we're doing is we're trying to use the evidence from a sample to make a decision as to whether we believe a claim is true or not. So there's always a risk that our evidence is pointing to the wrong decision. So the significance level, as I mentioned earlier, is something that researchers carefully choose based on the probability that they're willing to accept in making this type of error. So it's a kind of a delicate balance between risk and how strong your evidence will need to be. The most common significant levels, the most common alpha levels in statistic are 0.05, which is 5%, 0.01, which is 1%, and 0.10, which is 10%. Of these three significance levels, the 5% significance level is the most common. And if a significance level is not specified in a problem, we typically default to a 0.05 significance level. All right, I'm going to spend a little bit of time on this slide because there's a lot of good information here. In Chapter 8, I mentioned we're going to talk about two different types of hypothesis tests. In this first section, we're kind of just really laying down the foundation, but in sections 8.2 and 8.3, we're going to look at testing claims about a population proportion and then testing claims about a population mean. We will not, in this course at least, talk about testing claims about a standard deviation or variance for a population. So only the first three rows here will apply to us. In section 8.2, we're going to talk about claims made about a population proportion P. Know that all of those problems are going to involve the normal, the standard normal distribution, the distribution of z-scores. So if you've got a proportion, we're going to be working with z's. And the requirements really will always be met for the purposes of our course, but in practice, we want to make sure that the sample size times the claimed value of the population proportion, that exceeds 5 or is at least 5, and that the sample size times 1 minus P is also at least 5. The test statistic, let me move this down for just a minute. Almost cancel the recording. The test statistic that we kind of mentioned in our overview is going to be a z-score, but this is a different way of computing z. It's still counting standard deviation distance from the mean, but in the numerator we have the sample proportion p hat. So this is the proportion that we found within our sample. We're going to subtract from that the claimed value of the population proportion. So this lowercase p right here is that number that appears in our two hypotheses. And in the denominator, we will have the square root of p and q, where q is 1 minus p, so these two numbers add up to 1. Again, we're using the claimed value of p here, so it is that value that appears in the null hypothesis and in the alternative hypothesis. And then q is just 1 minus that number. N is our sample size. For section 8.3, we are going to be talking about testing claims regarding a population mean mu, there we actually will be using one or another when it comes to the distribution. Some problems will involve the normal, the standard normal distribution, the distribution of z-scores, and others will use the distribution of t-values. We're going to spend more time talking about this when we get to section 8.3. How we distinguish between which of the two test statistics to use is going to come down to whether the population standard deviation is somehow magically known or whether it more realistically is not known. So when I teach this class in person, I make a big stink about this. If we don't know the population mean, if we don't know mu, in practicality, we can't know sigma, because sigma, the population standard deviation, is calculated from mu. In fact, it's, referring to distance from the mean. So we use the standard normal distribution kind of as a stepping stone, kind of as using something that's known to us to start practicing with the process. But in reality, anytime we're talking about a population mean being unknown, we're going to be using t instead. The next part of the hypothesis test is to compute the test statistic and the corresponding p-value, or to compute the test statistic and compare it to a critical value. So we're getting toward the end of that graphic that we saw a little while back. A test statistic for our purposes is going to be either a z-score or a t-value, and it is going to be computed using those formulas that I showed you 2 slides back. So it's either a z-score or a t-statistic, and they will be calculated from our sample result. So if we're talking about a proportion, it's going to be calculated from the sample proportion. If we're talking about testing a claim about a mean, then it's going to be calculated from the sample mean. We will not be performing tests regarding standard deviation, so we're not going to worry about a sample standard deviation, but it's snuck in here in our notes. All right, so the z statistic or the t statistic is a calculation from our sample result with the assumption that the null hypothesis is true. So remember when I went through, let me see if I can go back. When I went through here, the z test statistic and the t test statistic is making the assumption that the population parameter has the value that appears in our hypotheses. So here the p that is included is the p that appears in our null hypothesis, and the mu that we are referencing here is the mean that is assumed or claimed in the hypotheses. All right, let's return to our example. So we have a claim that most internet users use two-factor authentication, and we have a sample size of 926. The sample proportion, so this is the result coming from our sample data, was 52%. Sometimes they'll give us the p-hat value, sometimes they'll give us x. So if they give us x, then p-hat is simply x divided by n. So if they had told us instead of 52%, they said it was actually, let me see what 52% of 926 is. So if they had told us 482 people from the sample used two-factor authentication, then we can convert it to a decimal here by doing the 482 divided by 926 rather. Now, our null hypothesis, we talked about this earlier, is that the proportion is exactly half, exactly 0.5. The alternative is that it is greater than 0.5. So we're going to use this P in calculating our test statistic, and when we're going to be using Q, which is 1 minus P, to calculate the test statistic as well. The test statistic turns out to be 1.22 if we use the manual formula, which is just fine. When we use the calculator, it gave us 1.25, which is still quite close to what we would get using the formula. So those of you who are not going to be using the formula, those of you who are not going to be using the calculator don't need to be too concerned about using the formula. You will get similar enough results that the decision that you reach at the end will be the same. All right, so our test statistic Z is 1.22. Now let's talk about how to compare the test statistic to a critical value. The critical region, also known as the rejection region, is the area corresponding to those values of the test statistic that would cause us to reject the null hypothesis. So when we're performing a hypothesis test, we're kind of secretly hoping that our test statistic does fall in the critical region, because our ultimate goal is to reject the null hypothesis. Remember, the null hypothesis is the counterclaim. So if we can reject the counterclaim, that makes it look pretty good for the original claim, right? Because by rejecting the counterclaim, we have evidence in support of the original claim. So in this slide, I'm going to briefly talk about the fact that there are 3 different types of hypothesis tests. The first is called a two-tailed test, and a two-tailed test is one where the alternative hypothesis includes that not equal to symbol. All right, you see that down here. In a two-tailed test, you have 2 critical regions. You have a critical region in the lower tail on the left and in the upper tail on the right. And those are mirror images of each other. A left tail test and a right tail test, these are called one-tailed tests. All right, so they're kind of grouped together as one-tailed tests. A left tail test is one, and I have these backwards. Ignore where my cursor is now, this one's correct. A left tail test includes the less than symbol, so this is incorrect here. And we're looking at the critical region only being in the left tail. A right tail test is one in which the alternative hypothesis uses the greater than symbol. So again, this is backwards. This is incorrect here where my cursor is. So we're looking at a critical region being only in the upper tail, in the right tail. So really, depending on which symbol is being used in the alternative hypothesis, that is what is going to determine whether we have a two-tailed test, left-tailed test, or a right-tailed test. And again, remember, this right here is backwards. The one under the picture is actually the correct one. Now, let's talk about the p-value method. With the p-value method, after we compute our test statistic, we are going to find the area that is under the curve that exceeds that test statistic. And by exceed, if the test statistic is in the right tail, then we're looking at area to the right. If the test statistic puts us in the left tail, then we're looking at area to the left. So we're looking at the area or the proportion that exceeds that test statistic. If we're looking at a two-tailed test, then we're going to take the area either in the left or the right tail and multiply it by 2 because of symmetry. We're going to see this played out in the next few slides. So back to our chapter problem, we had a test statistic of 1.25 if we use the calculator, or 1.22 if we use the manual formula. The calculator gave us a p-value equal to 0.1056. If we were to use the other technique by using the formula, we would get a slightly different p-value of 0.1059. So again, you might have some slight differences, but nothing that would lead you to different conclusions. So whether you're using the table or using technology, you should all reach the same conclusion. All right, let's look at this figure that summarizes what to do with the p-value, if that was the method that you chose to use. So if your test statistic is to the left of the center, to the left of the center of the curve, then the p-value is going to be the area to the left. Excuse me, I fast forwarded too fast. Is going to be the area to the left of that statistic if you have a left-tailed test. If you have a two-tailed test, then you're going to multiply that area by 2. Why? Because anything more extreme could be here or it could be here. So a two-tailed test is going to take that area and multiply it by 2, and that is what we would call the p-value. On the other hand, if your test statistic is over here to the right of the center, then the p-value will be the area to the right of that test statistic. And if you have a one-tailed test, that's it. It's just area to the right. So a left-tailed test would be area to the left or area to the right only. A two-tailed test would take whatever tail area you're finding and then mirroring that on the other side, so that essentially you're multiplying that area by 2. Now, I mentioned earlier there's a lot of P's going on here, and I want to clarify what each one stands for. A population proportion, that's our unknown population parameter that we're making some claim about, we're going to use the lowercase letter p. A sample proportion comes from the data obtained from a sample that we're going to label as p hat. So the hat symbol means this is a proportion for a sample. No hat symbol means we're talking about a proportion for the population. A p-value really should not have its own symbol because it is quite different than what these stand for. So I usually write p-value out completely by hand. However, we saw on the calculator results earlier that the p-value comes up on the screen as lowercase p, and that's unfortunate. So that p-value on the calculator shows up as lowercase p, but in fact it's a p-value, not population proportion. For the critical value method, again following the same chapter problem, once we found that z is equal to 1.25 or that z is equal to 1.22, we would compare it to a critical value that would be found in advance. The critical value comes directly from the significance level for your test. If you have a 10% significance level, you'll get a certain critical value. If you have a 5% significance level, you'll get a different critical value. This goes back to what you learned in Chapter 7 when you were constructing the confidence intervals. So for example, if we have a significance level equal to 5%, 0.05, then the corresponding critical value would be 1.645. And again, this goes back to what we talked about in Chapter 7. So 5% significance, we had a one-tailed test. There's 0.05 area. 0.05 area in this upper tail. We can work backwards to find what that z-score needs to be, or our table A2 already has the critical value written for us as 1.645. Well, the sample result, the sample proportion, didn't reach that critical value, because when we standardized it, when we converted it to a z-score, we got either 1.25 or 1.22. So our result did not make it into the critical region. Remember, that's kind of our secret hope, is that our sample result, when standardized, takes us into the critical region. Because if it were to fall in the critical region, then we would have claimed that we had evidence against the null hypothesis, and by default that means we have evidence in support of the alternative hypothesis. But in this case, we didn't quite meet the threshold. So our conclusion for this particular example is that we do not have enough evidence against the null hypothesis. We fail to reject the null hypothesis. So to make that decision using a p-value, what you would do is compare your p-value to your significance level. So if your p-value is less than or equal to alpha, you reject the null hypothesis. If your p-value is greater than alpha, then you fail to reject the null hypothesis. You might recall that the p-value that we found earlier was 0.1059 or 0.106 when we round. The significance level was 0.05. The p-value here exceeded the significance level. We want p-values to be small, small, small. P-values that are small, small, small give us indication that our evidence from our sample is strong, strong, strong. So the smaller the p-value, the stronger our evidence from the sample. So small p-values are what we hope for. We would have hoped for a p-value that is smaller than 0.05 for us to have claimed victory. And that didn't happen here. Our p-value was not smaller than our threshold, our predetermined threshold of 0.05. So again, using the p-value method, we would fail to reject the null hypothesis. That means that our sample result was not surprising. It's part of expected fluctuation. It was not significant. It was not extreme enough for us to have declared victory, that we found evidence that most internet users use two-factor authentication. Now, that statement may still be true, but our sample result just wasn't strong enough to support that claim. Now, there is some clear language that I want us all to agree on. There are only two ways to make a decision. Either we reject the null hypothesis or we fail to reject the null hypothesis. I want us to avoid using the words support or proof or indicates. I want us to say we have evidence to reject the null hypothesis, or we have insufficient evidence and therefore we fail to reject the null hypothesis. We always will make our decision in reference to the null hypothesis, even though the original claim was the alternative hypothesis. I know it's a little confusing, but the more we do this, the more you'll kind of fall into a rhythm. So your final decision at the end of a hypothesis test is either to reject the null hypothesis or to fail to reject the null hypothesis. Of course, we secretly hope that our evidence is strong and that it gives us enough grounds to reject the null hypothesis, because in rejecting the null hypothesis, we're kind of finding evidence in support of the alternative. We just want to kind of avoid that language. All right, so you'll see my write-up in a separate post, but I always like to take that final decision and translate it back into English, translate it back into the context of the problem. So reject H naught. What does that mean? In this case, we say we have insufficient evidence. We have insufficient evidence against the null hypothesis. So we have insufficient evidence to reject the claim that that the proportion of internet users who use two-factor authentication is exactly half, exactly 50%, exactly 0.5. We have insufficient evidence to reject that claim. That also means we have insufficient evidence to support the original claim that more than half did. Here is what our author is suggesting. There's not sufficient evidence to support the claim that most internet users utilize two-factor authentication. So here, Mr. Triola is choosing to write his interpretation in terms of how it relates to the alternative hypothesis. I just want to urge you to not do that and instead only refer to the null hypothesis. So here's a little bit more help in how to word your final conclusion. So it says, for help in wording the final conclusion, refer to the flowchart on the next slide, which lists the 4 possible circumstances and their corresponding conclusions. We're going to look at that in just a bit. Note that there is only one case that leads to wording indicating support for the original conclusion. If you want to support some claim, state it in such a way that it becomes the alternative hypothesis and then hope that the null hypothesis gets rejected. Lots going on in this slide, but basically, here's the question. Do you have enough evidence to reject the null hypothesis, or do you not have enough evidence to reject the null hypothesis? So if you don't have enough evidence to reject the null hypothesis, then you say there is not sufficient evidence to support the claim, blah, blah, blah. If you do have enough evidence to reject the null hypothesis, and say there is sufficient evidence, and I don't like the word support. You'll see my work, and that's what I hope you use to model and to imitate as you work on your own problems. There's a lot of manual write-up involved in Chapter 8. So while my math lab is going to give you the scenarios and it's going to kind of set up the problem for you, I really want you to practice writing these manually as opposed to only entering your answers in my math lab, because it's really watered down the way my math lab is asking you to do this. So I'm going to model this for you, and I hope that you take me up on my invitation to practice writing these out manually. Here is another slide talking about wording. The word accept is misleading because it may imply that we are proving something. A hypothesis test will never serve as a basis for proof. It only is going to tell us whether we believe our sample is providing the kind of evidence we were hoping for, or whether our sample was just not extreme enough to give us the strong enough evidence that we want. Yes, there are multiple negatives. So failing to reject, there's 2 negative words there, to fail and to reject. Failing to reject is an acknowledgement that our sample result just fell short. So I do, and statisticians do, prefer the double negative for that reason. It's an acknowledgement that we have failed to gather the kind of evidence that was necessary for us to reach a certain conclusion. Think about the court system in the United States. When a defendant goes to court, there are 2 possible verdicts. Either the defendant is found to be guilty, which is negative, right? Guilty is negative. Or the defendant is found to not be guilty. We never say innocent. We never say this person didn't do it. We just say the prosecution failed to gather the necessary evidence for a conviction. So it's an acknowledgement of the failure on the part of the prosecution. So that acquittal, that release of guilt really isn't an affirmative verdict. It's a double negative verdict, right? It's a not guilty versus innocent. Same goes here. We fail to reject is the preferred wording versus we accept. Finally, let's talk about some of the errors that can be made when performing a hypothesis test. Remember, we don't know the true value of the population parameter. If we knew it, we wouldn't have to test a claim about its value. So we never know exactly whether our procedure is going to lead to the right conclusion or not. There's a risk that we just got a really weird sample and that our sample result either wasn't extreme enough to show that something was actually there, or was unusually extreme. And so we reach a conclusion that really doesn't correspond with reality. So we're going to talk about two different types of possible errors, type 1 and type 2. A type 1 error is the mistake of rejecting the null hypothesis when the null hypothesis is actually true. And this happens when our sample result is extreme enough that we say we've got evidence against the null hypothesis. Well, sometimes we get extreme results just by luck, or in this case, by a lack of luck. So getting an extreme sample that leads us to reject the null hypothesis is not proof. Remember, it's just what the evidence indicates. And sometimes by fluke, we get a really extreme value. So the probability of making a type 1 error is equal to alpha, your significance level. Finally, a type 2 error is the mistake of failing to reject the null hypothesis when the null hypothesis is actually false. The probability of making a type 2 error is the Greek letter beta, and it's not too hard to calculate, but it's not as straightforward as just choosing the value in advance, like we would choose alpha at the beginning of a test. Of these two errors, depending on the context, most people would agree a type 2 error is more severe because it fails to get a sample that is extreme enough to say that there's actually something to it. If we think about medicine, for instance, a type 1 error might be equivalent to saying that a medicine is harmful and keeping it from the market just to be safe, when in fact it's not harmful. So the detriment here is that a potentially effective drug is kept from being released because we got some clinical trials that would indicate that there's a danger there that really isn't there, but we had evidence of it, and therefore just to play it safe, we decided not to approve it for public consumption. A type 2 error in the same scenario is that there is a dangerous drug, and that in our clinical trials, we just failed to detect the danger. The sample results from the clinical trials didn't pick up on the side effect, and the drug gets approved, it gets released, and then it causes a lot of harm. So you can see that in this scenario, type 2 error is more severe. Either case, know that both errors are possible and that there are risks involved in doing a hypothesis test when a decision is made contrary to reality. Here we have just a quick summary of the type 1 and type 2 error scenarios. Again, a type 1 error occurs when we reject a null hypothesis and in reality it happens to be true. A type 2 error happens when we fail to reject a null hypothesis and in fact the null hypothesis was false. Here's a little hint for describing the type 1 and type 2 errors. When we want to write these out as descriptions in words, we can say that a type 1 error happens when we reject the null hypothesis and we shouldn't have. A type 2 error happens when we fail to reject the null hypothesis and in fact it was false.